This is Unit 7 Rotation, video number 4 on the topic of rotational kinetic energy. So let's just recall what we remember about Unit 4 energy. So we studied energy, and there were a couple big ideas from energy. One was that work changes the energy of the system, and this is the equation from your reference tables. The change in energy is equal to the work done, which equals the force that causes the displacement times the displacement. And those two needed to be in the same direction. So we've got this parallel symbol here. And that's where that cosine theta comes from, just trying to prompt you to get the parallel component of the force, or the component of the force in the direction of the displacement. Our second big idea was that in a closed system, the total energy always remains the same. So the energy initially at some point in the system equals the energy at another point in the system if no work is done on the system. The third big idea was about power is the change in energy over time. That also still applies here. So all of the things that we remember about energy still apply here, but we have a new form of energy, and I'll just do a quick derivation of that. So our classic translational kinetic energy equation is 1/2 mv squared, but we want to think about things rotating. So we're going to think about, well, if the linear kinetic energy is 1/2 mv squared, we're going to replace the linear velocity with angular velocity times the radius. So the rotational kinetic energy is 1/2 m times angular velocity times the radius squared. So we'll distribute that squared to the angular velocity and the radius, and then we'll move that around to get our mr squared, which is the general equation for the moment of inertia of a rotating object, or of a point mass. So the rotational kinetic energy is equal to 1/2 of the moment of inertia times the angular velocity squared. And this is in your reference tables. So this is a new form of energy that we'll see in systems where something is rotating. Now we also need to talk about some terminology that the AP exam uses to discuss rotating or rolling objects. So for an object to roll, the question must state that there's a rough surface or that it rolls without friction or rolls without slipping. So this means that there's enough of a frictional force for a torque to be applied and cause angular acceleration, but because it's rolling and not sliding, we'll say that friction doesn't create heat or doesn't do negative work. So there's enough friction for it to roll, but not so much friction that we're losing energy from our system due to friction. So let's analyze what would happen because of friction when we're rolling down versus rolling up a ramp. So if we're rolling down a rough ramp, our angular velocity points in this direction. So it's rolling clockwise down the ramp, but the force of friction acts up the ramp to actually increase the angular velocity of the object. So that's going to cause a torque, it's going to cause an angular acceleration, and this object will speed up. So its angular velocity will speed up. So it will have a energy conservation formula of gravitational potential at the top, and then kinetic plus rotational kinetic more and more as it goes down. If it's going up the ramp, the angular velocity is in this direction, but friction will exert a torque up the ramp as well, and that will actually cause an angular acceleration that goes the other direction. So it's going to slow down as it, so the rotation rate slows, or the spin rotation rate slows due to the torque caused by the force of friction. So we have a object that had translational kinetic and rotational kinetic, and once it reaches the top of the ramp, it slows down and it stops, and it will only have gravitational potential at its maximum height that it has. So we're looking at these points in the context of, which thing is going to make it down the ramp first. So if we look at our kind of the setup that we have here, so which will reach the ground first? An ice cube, a solid sphere, a hoop, or an ice cube, a solid disk, a hoop, a solid sphere, or a hollow sphere. They all have the same mass, and they all roll without slipping. Well, in this case, the ice cube is going to reach the ground first because it's not going to roll. And that means no energy will be taken away from its linear kinetic energy. All of the gravitational potential energy will be turned into linear kinetic energy. So it's going to have the fastest speed as it goes down the ramp, and it will have the fastest time down the ramp. Now, if this whole ramp was frictionless, all of these objects would reach the ground at the same time, because there would be no friction to cause a change in the rotational kinetic energy, to cause a torque. So if this whole ramp was frictionless, none of these things would roll. They all have the same mass, so they're all going to reach the ground with the same speed and at the same time, because it's the same slope of the ramp. But the objects that roll are going to roll without slipping. So we've got a disk, a hoop, a solid sphere, and a hollow sphere. So which of those is going to reach the ground first? Well, that depends on the moment of inertia of those objects. So we want to look at our moment of inertia formulas from our chart in the textbook and on our homework set. So the one with the smallest moment of inertia is going to have the smallest rotational kinetic energy, and so it will reach the ground the fastest. So the one with the smallest moment of inertia is the solid sphere, and that is followed by the disk, the solid disk, and then the spherical shell, and then the cylindrical hoop. So which will reach the ground first? Well, the smallest moment of inertia. So the smallest moment of inertia is the solid sphere, which has that 2/5 mr squared. Then the solid disk, and then the hoop, and then the hollow sphere. So the largest moment of inertia is the hoop, and that would be last. The smallest moment of inertia is the solid sphere, and that would be first. So we're going to do a can race with canned food on Wednesday. So bring in your canned food and try to pick one that you think is going to make it down the ramp the fastest. So we can also look at this through the lens of the energy bar charts. So this is a little different way than we've done it with LOL diagrams, where the blue color shows the initial energy in the system and the yellow shows the final. So they all have the same initial kinetic energy in the system, but in the end, they have different amounts of rotational kinetic energy depending on their moments of inertia. So the one with the smallest rotational kinetic energy is the one with the smallest moment of inertia. So we can see that with a more mathematical analysis, and that's what we looked at with the AP workbook questions. So you can look in the OneNote at, it says like rotational kinetic energy analysis, to see how we worked through a derivation of the speed they would have at the bottom depending on their moment of inertia. And if there's interest, I can make a video